This is a lecture from Open Tuition. To benefit from the lecture, you should download the free lecture notes from opentuition.com.
All right, we're still on the chapter measures of average and dispersion. And in the previous two lectures, we looked at the various measures of average, arithmetic mean, median, mode. In this last lecture on this chapter, we're going to look at measures of dispersion. Now, what we mean by that, now dispersion is another word for spread. And the relevance is this. Just let me give you a very, very tiny example before we look at full ones. Suppose we'd collected some data, I don't know, people's wages or something, and there were three observations, 990, 1,000 and 1,010. And if I said to you, what's the arithmetic mean, the average, add them together and divide by 3, and the average, the arithmetic mean, is 1,000. No problem. But suppose I went somewhere else and found out what people's wages were, and there were three observations, and it was 100, 1,000, and 1,900. And I said, again, what's the arithmetic mean? By all means check me, but add them together and divide by 3. And again, the arithmetic mean, or x bar, is again 1,000. So both samples there have the same average. And yet there is a very big difference. In the first sample, whoever we pick is going to be very, very close to the average of 1,000. Whereas in the second sample, the average is 1,000, but of course, whoever we pick could be a lot further away. There's a bigger spread of the observations. Now, there are only 3 there, obviously, just a tiny illustration. But certainly if you come to look at probabilities, if I say in the first case, what's the probability of somebody earning more than 1,500? It's 0. Because they only earn 90, 1,000, 1,010. They all earn almost 1,000. But if I say in the second case, what's the chance of somebody earning more than 1,500? Well, it's a lot bigger. You know, there are people earning 1,900 there. And so, certainly when we come in the next chapter to look at things to do with the probabilities, things, when we look at a sample, we don't just need to know the average. It's the same there in both. But it's also going to be of interest to know the spread. In our sample, how likely are they to be very close to the average, or how likely are they to be much further away? So that's what we mean by dispersion, the spread. And that's what we're looking here at, different ways of measuring. And there are 4 things you need to be aware of. They're listed there: range, variance, standard deviation, coefficient of variation. Let me explain what they are. Again, I'm going to use the examples from the earlier in the chapter, example 2 where we had discrete variables, example 3 where we had continuous. And so I'll explain with both of them. And hopefully you've still got the previous examples in front of you. If not, you'll have to look back. First of all, the example 4, discrete variables, where we're looking at the information in example 2, where we had the observations and number of complaints was 0, 1, 2, and 3. And the frequency, the number of weeks in which we had each number of complaints, the frequency 1, 6, 4, and 2. 7, 11. Yeah, we looked at 13 weeks. We worked out before what the arithmetic mean was, and for what's following, it's only the arithmetic mean that's of any interest. So the arithmetic mean or x bar, I'm looking back, it was 1.54. That was the average. Well, we want a measure of how, although the average is 1.54, how big is the spread within the sample? Well, the range is the easiest of all and always the easiest. It's simply, I'm not going to write down, it's the difference between the highest and lowest of the observations. So here, the highest observation was 3, the lowest was 0, so the range is 3. These are all, I think, well, no, these are complaints, sorry. Oh. So that's all nice and easy, it's always easy. The next one is the variance. Now this is a little bit more interesting, because although the range is 3, the actual observations were 0, 1, 2 or 3. We know what the average is, and so we're going to take the average distance away, or deviation, from the mean. Let me show you what I mean. The first observation was 0. How far away is that from the average? Well, it's 1.5, the average was 1.54, so 0 is minus 1.54 away. It's, if you want, x minus x bar, the difference from the observation from the average. What about 1? Well, the average was 1.54, so 1 is below, it's minus 0.54 from the average. 2 is above the average. 2 minus 1.54, it's plus 0.46. 1.54 plus 0.46 is 2. And finally, 3. 3 minus 1.54 is 1.46. So as you'd expect, some observations are below the average, minus 1.54, minus 0.54. Other observations are above the average. I want to know the average difference from the mean. We could take the average as they stand and say, 1 is that much away, 6 is that much away, and so on. The only problem is, if we took an average of those in the normal way, multiply by 1, 6, 4, 2, and get the total and divide by 13, because of the minus and plus signs, try it yourself, but you'd end up with 0. You know, 1 times that is minus 1.54, 6 times that is minus 3.24, 4 times that is, well, I'll finish it off since I'm there, 4 times that is 1 plus 1.84. 2 times 1.46 is plus 2.92. And to take an average, you'd add them up and divide by 13. Well, if you add them up, minus 1.54 minus 1.84 plus, sorry, start again, minus 1.54 minus 3.24 plus 1.84 plus 2.92, we end up, well, effectively with 0. The reason I get minus 0.02 is because of the rounding before. But effectively, they're going to add up to 0. They must do. There are as many below as there are above. And so that doesn't tell us very much. And it's because of the sign problem. The minuses cancel out the pluses. And so the way we standardly get round it is we square those differences. Because you should know from school, if you square a negative number, it becomes positive. So we get rid of the sign problem. And we take an average of those. Square them and average. To average, we multiply by the frequency and we'll divide the total by 13. but we're taking an average of the squares of the differences. And so let's do it. 1.54 squared times 1 is 2.3716. 0.54 squared times 6 is 1.7496. 0.46 squared times 4 is 0.8464. And finally, 1.46 squared times frequency of 2 is 4.2632. And if we get the total of them, sigma fx minus x bar squared, but I'm not too worried about the symbols, but the total of those, again, this time they're all positive because we're squared. So 2.3716 plus 1.7496 plus 0.8464 plus 4.2632. Error. Start again, sorry. 2.3716 plus 1.7496 plus 0.8464, 4.2632. I get 9.2308. Remember what I'm doing? We're taking an average of the squares of those differences. So for the average, multiply by the frequency and divide the total by the number of observations, which is 9.2308 divided by 13. 9.2308 divided by 13 is 0.7100. So as I said earlier, normally, unless you're told different, do things to two places. What is that 0.71? That 0.71, again, is the average of the squares of these differences. So you know the difference, 0.54, 0.46, 1.54, 1.46. The average of the squares of them is 0.71, and that's called the variance. Excuse me. And I'm sure you can see, I mean, we'll check when we do the next example as well, that the bigger the spread, you know, had this gone anything from 0 to 20 instead of 0 to 3, the bigger the spread, the bigger this variance will be. It's a measure of the average spread. The only problem with that, and the reason we don't actually use that very often, is to think back to what we were looking at. The observations were numbers of errors. And we took the differences from the average, so it was minus 1.54 errors, minus 0.54 errors, and so on. But then we squared them all and took the average. And so the variance is 0.71. It's sort of errors squared, which is a bit odd. You know, the observations were errors, and now we're talking about errors squared. Now, again, it is a measure of spread. The bigger the variance, the bigger the spread. But much more commonly, to get back to the same units, which here is errors, we take the square root. The standard deviation, and this is the most important one of all, I don't think we'll need the symbol in the exam, but just in case, it's sigma, small sigma. The standard deviation is the square root of the variance. So we still need all the workings we've just done. But whereas the variance is 0.71, the standard deviation is the square root of that, which is square root 0.71. If I keep this again to 2 decimal places, it's 0.84. And we are back to the same units. The observations were errors. The differences were numbers of errors, but we'd squared them. So the variance, as I said, was like squared errors. By taking the square root, we're back to errors. Now, standard deviation, which is the vital one for the exam, even though you can be asked any of these, you'll see in the next chapter how we can make terribly important use of it. But for the moment, it's a measure of spread. The more the spread is, the bigger the standard deviation, the bigger the variance will be, and the bigger, therefore, the standard deviation will be. One more, which is less important, but just could be relevant, is something called the coefficient of variation. And before I write down what it is, let me explain sort of the importance of it. Is 0.84 a big spread or a small spread? Well, I don't know. I mean, here our average was 1.54. Suppose the average, a completely different question, suppose the average had been 15.4, but the standard deviation was still 0.84. The point is, the bigger the mean is, the bigger the observations are, the bigger a spread you'd accept. So if the average was 15.44, I'd in a sense be willing to accept a bigger standard deviation. And so coefficient of variation relates the two together. We still need all the workings we've done, but once you've done it, it's very easy. The coefficient of variation is simply the standard deviation divided by the arithmetic mean. Or if you want symbols, sigma divided by x bar. So again, we still need all that arithmetic we've done, but the standard deviation is 0.84. The arithmetic mean, I think, was 1.54, yes, 1.54. And so the coefficient of variation is again, if I round to 2 places, it's 0.55. So it just could be useful. As I say, if suppose the observation, I hope I've already explained it, but just to make sure, suppose the observations, instead of being 0, 1, 2, 3, they'd be 0, 10, 20, 30. You know, you'd end up with a much bigger mean, 10 times as big. You'd end up with a much bigger standard deviation. But with bigger observations, I'm not surprised there's a bigger standard deviation. The coefficient of variation sort of puts the two together. And I can't get up the screen again. This sidebar's daft. Anyway, there we are. Oh, dear. So there are the four, I beg your pardon. Range, very easy, difference between top and bottom. Variance, I'm not going to talk through all the arithmetic again, but the average of the squares of the deviations. Most important of all, standard deviation, the square root of the variance. And finally, less likely, but coefficient of variation, standard deviation over the mean. Well, that is it, but since we did have, what was it, example number 3, we had a continuous distribution. Let's do example 5, which is getting the same 4 measures, range, variance, standard deviation, coefficient of variation, but on a continuous distribution. And in fact, what might be a good idea here, although I'll do it on the screen, the rules are exactly the same as the one we've just done. But as we did earlier when we looked at the mean, we use the midpoint to represent the range. So it may be ideal if you had to go yourself and then, I'll pause the lecture, had to go yourself and then checked. But I'll work through it. It was 0 to 500, 500 to 1,000, 1,000 to 1,500, 1,500 to 2,000, 2,000 to 2,500, 2,500 to 3,000. And the frequency of the observations, 1, 4, 8, 19, 14, 6. Now I say midpoints represent the range. The one exception is the overall range, the difference between the highest and lowest value. Well, even though it's in split into ranges here, we say the lowest value, it started from 0, the highest is 3,000. So the range, we'd say, was 3,000, and here it's dollars. For all the others, we do what we did before. We let the midpoint represent the range. So 0 to 500 is 250, 1250, 750, 1250, 1750, 250, 750. And we carry on just as I did with the last example. If you look back, I'm not going to waste time here, we already worked out the arithmetic mean. The arithmetic mean, or x bar, excuse me, I'm looking back to example 3. Yes, we got 1,817. And so now let's work out the variance. Using the midpoint to represent the range, the difference between the observations and the average. So 250 minus 1817 is minus 1567. 750 minus 1817 is minus 1067. 1250 minus 1817 is minus 567. 1750 minus 1817 minus 67. 2250 minus 1817. 433 positive. And finally 2750 minus 1817 plus 933. So obviously at bigger numbers it's taking longer, but it's exactly the same approach. We want the average, but for the reasons I explained before, instead of just averaging x minus x bar, the deviations, we square it, or square them, multiplied by the frequency, so as to be able to take an average. So 1567 squared times 1 is 2455489. 1067 squared times 4, 4553956, 567 squared times 8, 2571912, 67 squared times 19, 85291, 433 squared times 14, 2624846, and finally 933 squared times 6, 5222934. Now, I hope you did have a go yourself first. I'm bound to make an arithmetic mistake, but anyway. The total sigma fx. Here we go. 2455489 plus 4553956 plus 2751912, 85291, 2624846, 5222934. I hope I'm right. I get 1769448. And so to get the average of these squares of the variance, divide by the total number of observations, sigma f, the variance 1769448 divided by 52 340,277. Now I'm pretty sure I've made a mistake somewhere there, but I'm not going to go back and check. Divided by 52. 34027. Yeah, I think I may have made a mistake earlier on there, but there's a printed answer in the notes anyway. I'm more concerned that you follow the approach. However, although subject to my arithmetic, there's the variance. The problem again, think about it, the original observations were dollars. The differences were all in dollars, but we've now got dollars squared. And so for the standard deviation, which, as stressed before, this is the important one. To get back to the same units, to get back to dollars, we take the square root of the variance, the square root of 340277, and we are back to dollars. So the square root I get 583. Now, can I repeat? I may well have made an arithmetic error earlier on. If I did, don't all start writing comments telling me. My approach is right. I'm not going to waste your time and my time going back checking every single figure. So there's nothing extra to learn from what we did in the in example 4. But clearly, there's a lot more numbers involved. It takes that bit longer. Finally, and here now it might make a bit more sense what I said about coefficient of variation earlier. Here, the standard deviation is much bigger than last time. You know, last time, standard deviation was tiny. It was 0.54 or something. Yeah, 0.55. But of course, the average was a lot smaller. The arithmetic mean last time was 1.54, I think. Here, the arithmetic mean was, where were we, 1817. Sorry, we're going all over the place here. What am I doing? Yeah, here the arithmetic mean was 1817. And so, although it's something we rarely use, in case it's asked for, the coefficient of variation, as before, is the standard deviation over the mean. Standard deviation 583. The mean again, 1817, I think, was it? Yes, 1817. And so, what does that come to? 0.32. So, there we are. All right, well, we've been through the arithmetic needed and everything we've been through in this chapter, although all of it's needed, median, mode, range, or can be needed in the exam, the two most important by a long way are the arithmetic mean and the standard deviation. In the next chapter, which is called the normal distribution, I'll explain why this is so important and show you, well, the various ways in which you can be tested on it.